Hello and welcome to this video on the Littlewood-Offord problem. It's a famous problem about, I guess, that Littlewood and Offord came across when they were studying zeros of random polynomials. But really, it's a combinatorial problem, and we're going to talk about just it kind of like as a puzzle with real numbers. So I read about it in this book by Bollobás called Combinatorics. It's a little textbook, and it's a famous problem, but I looked on YouTube and I couldn't find something that just like does the basic thing. I think if you look up Littlewood-Offord, there are videos that tell you about like current research in the area and stuff, which is super cool. But I just want to talk about like it in its most basic form, and in particular a proof by Erdős in the real case. And yeah, and these are like I'm gonna try to keep it sort of as elementary as possible. So I might go a little too slow for some of you out there. But what I'll do is I will, if I get the technology right, I'll get it to have like labeled parts of the video so you can kind of like skip things that you think you already know. Also, my writing can be a bit messy, but I will hope to post this slide thing and type notes in the description so you can follow those instead of this if it's really too bad. Okay, so with that out of the way, let's get started. So what is the Littlewood-Offord problem? Okay, so we're going to state it in kind of a special case. We're going to deal with real numbers. So let x1, x2, all the way through xn be real numbers. And all of them have absolute value greater than 1. So for all I, their absolute value is, I think it's greater than equal to 1, at least 1. Okay, and then there are, if you notice, there's n numbers, so there's 2 to the n different sums, right? So one of them could be like x1 plus x3 plus x4. That's one of the sums, right? But you could have just the empty sum, that's 0, stuff like that. And there's 2 to the n different ways. That's a big thing. 2 to the n different sums. And what we want to know is how many differ by less than 1. So let's draw a picture of what's happening. So I'm going to draw, so we know kind of this is the real line, and here's 0. And I'm going to draw the sums. So we know we have the empty sum, which is 0. So there's 1 right there. And then there's a bunch of other sums. And we said all of these xi's are greater than equal to 1. So we're going to say they're, here, I'll draw the sums in green. So one of the sums is here, and the xi's are outside. So for example, this could be x1 maybe. Maybe this is x2. But maybe x1 plus x2 is in here. x1 plus x2. And the Littlewood-Offord problem asks how many are, like, can you draw a ball of size, like a ball, a cluster of them, so that any 2 of them differ by less than 1. I don't know what that would look like. It's kind of like a cluster, and you pick, let's say, this ball. Any 2 within there are differ by less than 1. That's obviously not possible. It's not to scale, but you get the idea, right? Okay, and so to solve this, actually, we need something kind of completely different, and we need some notions about chains and antichains in a partially ordered set. So we're going to talk about something completely different now. Okay, so let X be a set of size n. And when I have a set of size n, like it's easier to just literally make them 1 through n, make the elements 1 through n. So I'm going to say that x is equal to 1 to, right? There is a natural order between the subsets of x. So there is an order induced by on subsets by inclusion, right? And this is a partial order. So what I mean by that, we all know, like, the most famous order is on like say the integers, right? We have 1, 2, 3, 4, and I'm drawing them like this to tell you that 3 is greater than 1 because it's above 1. 4 is greater than 1, 2 is greater than 1, that kind of thing. 4 is greater than 3, stuff like that. But when the order that we have on the subsets is not a total order like this, it's a partial order. And I think the best way to see that is just by like an example. So for example, if we take x equals 1, 2, 3, say that's x, right? And then, well, we have these other subsets here that maybe this will say is 1, 2, and this is 1, 3, and this is 2, 3. And then, like, we'll put those ones of size 1 here, so 1's there, 2, 3, and this is the empty set. Sometimes you denote it like that. Right, so what's the ordering between these? Well, we said the order is induced by inclusion, right? So the empty set's included in all these guys because, well, it has nothing, so it's definitely included in all these sets. What about 1? Well, 1 is included in this one. It's also included in that one. 2 is included in this one, and that one. 3 is here and here. And then these guys are all contained in the full mother set. Okay, so that'd be like a partial order. And, you know, you can see kind of that this guy contains this guy because you can kind of walk like that. But this guy and this guy are not comparable, right? 1, 3 does not contain 2, but 2 also doesn't contain 1, 3. There's no way to compare those two points in this partially ordered set. Okay, so we're gonna need some definitions. So a chain is a collection of subsets A1, A2 through AK, such that you have this A1 is a subset of A2 is a subset of ... AK. And what does that look like in the picture? Here, let me put my pointer again. So a chain looks something like this. That's a chain, right? So this would be A1, this is A2, A3, A4. And we have sort of inclusion all the way. We'll say a chain is maximal if no set can be added without breaking chain property. Right? So what does that mean? So this is a chain, but it's not maximal because we can add this guy to it. And this still isn't maximal because we can add this guy to it. But once we're here, this is maximal, right? Because if we add any other set, say we add this one, well, that breaks the chain property, right? Because this guy and this guy can't be contained, can't be compared. So this is no longer a chain. Okay? So because this picture is actually so useful, I'm going to copy it onto the next page. And we're going to introduce another definition that's kind of the opposite of a chain. And it's for that reason, it's called an antichain. So an antichain is a set, a collection, A1, A2, K, such that, so my writing is really bad, such that if I is not equal to J, then AI is not contained in AJ, and the other way around, but you can just flip the roles of I and J in this. Okay, it's somewhat more complicated definition, but it's a really simple concept. It's the opposite of a chain. So it's a set of points that no two of them are comparable. So like this, that's not an anti-chain, right? Because this guy is contained in that guy, right? But this would be an anti-chain. That's fine. And like we said before, this is actually an anti-chain, right? So like a question would be how big can a chain be, right? So we had this idea of maximal chains. So you kind of can keep like gobbling guys up until you're maximal, and then how big is this chain? Well, that's actually a really easy question, right? How big can a chain be? Right? It's kind of an easy question. It just turns out to be x plus 1. So x had 3 elements, and you just add 1 because of the empty set. And so a chain can be 4 points big, basically, in this case. But if x is bigger, it could have more. If x had 9 elements, you could have a 10 set chain, right? The question is a little bit harder for antichains, right? So I mean, you can kind of look at everything on one level, right? That's definitely an antichain, right? Because this guy is definitely not going to be containing that guy. If you have 2 sets of the same size and they're not the same, one can't possibly be in the other. So you take all the sets on one level. And how big can one of these be? Well, actually, so this is a good place to kind of stop and think about how many. So if x is equal to 1, 2, through n, right? We'll say, let's use this notation, x to the k, okay? This is like subset of size k. I don't know if that's a good notation or not. Maybe I'm just, I don't know if I'm like using the same notation as the book or whatever. We'll say how many subsets of size k are there? Well, there's n elements and we want to choose k of them, right? So there's actually something in math for that, right? So we have n choose k. If you haven't seen this before, this is the formula. With n objects, you pick k of them, and then you pick the k of them can come in any order. The other n minus k can come in any order. So that's why we take the factorial. I don't know how deep you want to go into this, but if you haven't seen n factorial, it's n times n minus 1, n minus 2, like, and so on. But okay, so what we know is we can always take everything of one level, right? So we can just choose we can choose I that's in between 0 and n, and we can just take n choose I elements all on the same level, and that's gonna be an anti-chain. And how big can this be? I'm just gonna state it without proof, but the biggest it can be is when I is n over 2. And because n could be odd, we're just gonna round it down. Okay, so like, I don't know how to draw this. In the case where it's 3, you can see it obviously gets bigger in the middle and then smaller again. So in general, it kind of looks like this. So say we have like lots of points. I don't know, say n is like really big. It kind of goes like this. There's like a couple of points here, way more points here, and then like kind of an explosion in the middle. It's going off to the left also. I just can't draw them. And then it tapers back down to how many sets are of the size. So, you know, when it's n over 2, you really get a lot of sets here. Okay? So we know that an anti-chain can be, the size of an anti-chain is at least n choose n over 2. Because we can just pick, that's an anti-chain. Everything at that level is n choose, there's n choose n over 2 of them. But it turns out that actually this is the best we can do. So there's a theorem, it's called Sperner's theorem. Sperner's theorem, so it's let x, x is 1 to n, and let f be an anti-chain of subsets of x. Then size of f is less than equal to n choose n over 2. Okay, and so we're gonna prove this. It's this was proved by Sperner. I don't know his first name, but it was in 1928, I think. And yeah, so we're going to prove this, and we're going to prove it. The proof is by double counting. So the general approach to double counting is you try to count something, or in this case, we're not counting exactly, but we're bounding a number by counting something in between. So in this case, what we're going to do is we're going to count number of pairs CA, where C is a maximal chain and A is in F, but A is also in C. So A is in F intersection C. Okay. So we're gonna count this in two ways. Okay, so number one. So the first way. So we want to. So how many pairs can there be? Well, first of all, how many maximal chains can there be? Right. A maximal chain looks like this. A maximal chain always starts with the empty set, right? And then there's some x1, and then there's x1, x2, and I'm writing x1 because this could be anything in 1 through n. And then x2 is something that's different from the first one, but anything could be anything in 1 through n. And then eventually you have x, and that's just everything, right? x1, x2, xn, and this is equal to 1, 2 through n, but in some order. So really, this is a maximal chain, and each one is a unique chain, right? If we chose x2 first, then the next step we chose x1, x2. Well, it's still a different chain because in this one, x1 came first, in the other one, x2 comes first. So any permutation of 1 through n, gives a unique chain. And so that's exactly how many chains are. There are n factorial chains, maximal chains. They're n factorial maximal chains C. Okay, well, how many of these? And then each chain can actually only have one element of an antichain, right? So we're counting pairs CA, and A is in an antichain F, right? This chain C, like we just look at this chain C, it can't possibly contain more than one element of F, right? Imagine if it did, like if we say this guy's an F, and this guy also is an F. These two guys are an F. Well, that's not possible because this one's contained. And so that wouldn't be an antichain, right? So they're n factorial maximal chain C, and actually, since each one only contains one element of A at most, that means that there are at most n factorial pairs CA. Okay, so we have one way of counting it. Okay, second way of counting it, and it being the number of pairs. Second way is, let's fix an A. So let's fix some A inside our antichain F. How many maximal chains actually contain A? Well, let's say A, it has K elements. We don't know what they are, but we're going to call them x1, x2 through xk. Okay, let's say it has these K elements. Well, what the chain looks like is it starts with the empty set, then we have something, question mark, and then something, question mark, right? And it goes on. And then it has A, and A is equal to x1, x2, xk, right? So somehow all these guys were added into the sets, but they could have come in any order, right? It could have been x2 first, then maybe it was x3, so x2, then x3, and then dot, 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 and then eventually you get A. So there's k factorial ways to put the k elements in, right? But the chain has to continue, and eventually you get the whole set X. So then there's n minus k elements is going to add, and they can come in any order. So there's k factorial times n minus k factorial ways that A can belong to a chain. Okay, so the number of pairs, okay, summing over all A, we can take a sum of all A in F. K, so K is the size of A. I don't want to write K inside this formula, but K is the size of A over here. So it's size of a factorial times n minus size of a factorial, right? And we sum over all a and f. But remember that, oh, and okay, well, here now we use the fact that we've double counted, right? So this is actually the number of pairs, and it's less than equal to n factorial by the first way that we counted. Okay. And now we can divide by n factorial. So we divide, I'm not going to rewrite it. I'm literally just going to divide. Divide on both sides. Okay. And what do we get? So this thing, it might look familiar. It's actually the formula for n choose k, right? But it's upside down. If you notice, it's actually upside down. So what has happened? It's the sum over all a and f. We get, it's n choose the size of a, but it's upside down, so it's to the -1. And this is less than or equal to 1, right? And then I'm gonna actually move this a little bit over, because what did we say before? We made the observation that whatever this choose guy is, and choose a, it's biggest, it's largest when the size of a is equal to n over 2, round down, right? So it doesn't really matter. Like we can just, if we just want to make a bound, we can say, well, this is bigger than if these were really big. So we can just sum over all a and f of n choose n over 2. And I tried to divide by not dividing. This is a choose to the -1. But now, look, we're summing over all a, but we have the same thing here. So we don't actually need this sum anymore, right? So it's the same as the size of f over n, and n choose n over 2. All right, and now we're done. Let's multiply n over 2 on both sides, and we get that the size of f is less than or equal to n choose n over 2, which is exactly what we wanted to prove, right? That's what I claimed in the theorem. That's what we wanted to prove. Okay, so we just proved Sperner's theorem. It's actually a really simple theorem to prove, and it's actually a really useful theorem. And well, in particular, it's useful to our Littlewood-Offord problem. So let's come back to this. We have x1 through xn, and they're real numbers with absolute value greater than or equal to 1. There's 2 to the nth sums, and how many differ by less than 1? Right? This doesn't even sound like, we're not even in the same ballpark. Here we have real numbers on a real number line. We're subtracting things, and here we have sets and chains and antichains. How do we link the two problems? Well, so I don't know if I mentioned, the Littlewood-Offord problem was first formulated by Littlewood and Offord, naturally, in 1943. And they were studying random polynomials, and they wanted to know the question for n complex numbers. And then they got a bound that was useful for them, but wasn't the best possible bound. It was just like, in 1943, they did what they needed to do. It was like they were interested in something else. But they asked this question, like, is there a best possible bound? And Erdős, Paul Erdős, he didn't prove it for complex numbers, but for real numbers, he's like, you can apply Sperner's theorem right away. So this is what he did. So, I mean, it's technically a lemma. It's a lemma. But this is by Erdős in 1945. So I guess 2 years have passed. Okay, let's just restate the whole thing. So let x1, x2 to xn be real numbers and the absolute value of all of them is greater than or equal to 1. At most, n choose n over 2 of their sums can differ by less than 1. All right, so I mean, this guy's popping up, n choose n over 2, so we know that Sperner's theorem is going to come in. But exactly how? Well, okay, so let's prove this. Let's prove this theorem. Okay, so the first thing we note is that these are all real numbers, and here's what they look like on a number line. These are all real numbers, and their absolute value is greater than equal to 1. So this is 1, this is -1. And greater than equal to, so they can be at 1, or they can be at -1, but they can't be in between, right? So they have to be outside. We can actually assume that all of them are on the right side. We can assume that they're all positive. And this is like a little bit mysterious when you first think about it. And yeah, I had to just like work out an example to like kind of convince myself that it's possible. But what you do is, okay, so what we're gonna do is we're gonna let, if A, okay, I'm gonna let X, I can write the word proof. Okay, proof. Okay, let X be 1 through N. Okay, and then for A, subset of X, so this is a subset of 1 through N, we'll let XA, okay, be the sum over all I in A, XI. So what does that mean? For example, if X is 1, 2, 3, right, and A is equal to 1, 3, then XA is X1 plus X3. So you pick all the guys in A and you add them together. That's what this is saying. Okay, so now we're linking these numbers, the sums of the numbers, with the sets, right? So we're heading on the right track. Okay, and what I said is that actually we can just assume it doesn't change the problem if we take all the xi's to be positive. And why is that? Okay, so this is a little bit like black magic, but we introduced this little triangle operator that takes a set A and a set B, and this is the symmetric difference. So it's equal to A union B, but you take out A intersection B. So in a Venn diagram that looks like this. This is A, this is B. We take A union B, right? So that would be the whole thing. But we take out, we actually don't want the intersection. So everything that's in A or in B, but not in both. Okay? It turns out that if you replace xi by minus xi, then what happens is everything gets shifted up by xi, and there's a permutation of these xa's that takes xa to xa symmetric difference with I. So the differences don't change, right? We're actually trying to figure out the differences between them. So it doesn't matter if everything is shifted up by 4, right? Like it just doesn't matter because, you know, even though the numbers are different, their differences stay the same. So that's exactly what this is saying. It's saying that if you, if xi is replaced by minus xi, then we have this permutation, and all the sums increase by xi. Okay, and like I don't know if I'm belaboring this point. I'll probably actually put it in a little have a little section in it so you can skip this if you want or something. But I'm actually just gonna do an example because it seems a little weird, right? So I'm gonna take 4 minutes and do this example. So say x1 is equal to 2.3, x2 is equal 1.1, x3 is equal to minus 4.1. Okay? So one of them is minus, and we're saying that if we replace that, then nothing changes. But first of all, what are the 8 different sums? So there's 2 to the 3 different sums, right? We have the empty set, that's always a 0. If we just take 1, well, obviously that's just x1, so it's 2.3. x2 is 1.1, and x3 is minus 4.1, right? And now we do the other combinations. So x1, 2 is 3.4, and x1, 3 is minus 1.8, x2, 3 is minus 3, and x1, 2, and 3, as you add all of them together, you get minus 0.7. Okay. Now I'm saying, okay, let's change it. So we replace x3 with positive 4.1. So now x1 is equal to 2.3, x2 is the same, 4.1. x3 is now 4.1. What happens to everything? Well, you can see that, I mean, like, they're not just gonna all increase by 4.1, right? They have to get shuffled around a bit. But what we're saying is we take the, if this is like XA, if we take XA symmetric difference with 3, then they increase by 4.1 exactly. So what does that mean? So the empty set symmetric difference with 3, you take a union with 3 and you take out what's in the intersection, but nothing was in the intersection, so it's just 3. This is 4.1, right? 4.1. And likewise, 1 symmetric difference 3 is 1, 3. And this becomes 6.4, and I'm just gonna write them all out, and you can, I don't know, twiddle your thumbs or something, or try to convince yourself why this works. This is the empty set. 0, x, 1, 2, 3. It works if you break it up into cases. Like, what happens if you actually do add 3? What happens if 3 was already there, then you have to take it away, right? But then you're actually taking away something that was negative. So that's why it works. Okay, so I've belabored this point now. Okay, so yeah, you can pause it here if you still want to see this. Otherwise, I don't actually need this page, so I'm going to read it. Yeah, okay, so if all the xi's are replaced by minus xi's, then all the sums increase by this, so it doesn't change the problem, right? So we can say they're all positive real numbers. That's what that whole tangent was about. Okay, so what do we do? Okay, let's let f be a collection of subsets, be a collection of subsets of x and x's 1 through n, such that, okay, if a and b are in F, then xa minus xb is less than 1, right? Less than 1. Okay, so I'm using this letter F, so this suggests that this might be an anti-chain, right? And that is actually, in fact, the case. So why is this an anti-chain? Well, if A is a subset of B, and A is not equal to B, okay, then remember we said all the x's are now positive, right? So xa minus xb is actually equal to xb minus xa because they're all positive now, and this is a sum. And this sum is bigger than that one because b is a bigger set. Right, let me write it out. Xb minus xa is equal to the sum of all I in b, xi. It's also minus the sum of all I in a, xi. And since a is a subset of b, this is the sum of all I in b set minus a, xi. But this is just another set, right? This is one of the sums above. This is just one of these sums, right? So what this means is this is just a sum of positive real numbers of that are actually have absolute value greater than or equal to 1. So this thing is greater than or equal to 1. Right? Also, b and a are not equal, so this is not empty. If this was empty, it would be 0, but this is not empty. It's greater than or equal to 1. So what does that mean? If xa minus xb is less than or equal to 1, sorry, greater than or equal to 1. It's greater than or equal to 1. Well, then a and b can't both be in F. So at most 1 of a, b is in F. Now we apply the theorem by Sperner. The size of F is at most, and choose n over 2 because F is an antichain. And that's it. That's so it's kind of interesting, right? So we have these real numbers, and they're all outside this unit ball. And if we form their sums, well, they no more than n choose n over 2. N choose n over 2 can differ from each other by less than 1. It's not that good of a bound because there's actually 2 to the n sums. And n choose n over 2 is actually, it's something like 2 to the n over square root n. So like, it's not that great. I mean, still 2 to the n over square root n can be together. But you know, I mean, there's this square root n. So it's like sort of the fraction that could be close is like 1 over square root n of them can be close. When n gets really big, it gets small. So yeah, okay, it's a pretty good bound. Okay, and I guess this wouldn't be a good video without a little exercise. So I'm gonna just state another thing that is so I'm gonna state another thing. Let x1, xn be real. Xi is greater than 1. Same setup as before. Now instead of choosing some of them and then summing them together, we always sum all of them. So there's 2 to the n sums of it's I equals 1 to n. It's all the xi's. But we add an epsilon I. And now epsilon I can either be -1 or 1. So obviously there's 2 to the n ways of choosing whether they're -1 or 1. And now let x be real. And so x also has to have this condition. How, or, you know, yeah, I'll just ask you this question. How many of the sums can be at distance less than 1 from x? And the answer is n choose n over 2. And so you're gonna, this is actually an equivalent statement to this lemma. So you can actually prove it directly from this lemma by doing some shifting. That's the end. Or you could prove it directly from Sperner's theorem, but like you don't have to because they're actually equivalent. You can even prove the lemma from this exercise. But yeah, there's some work involved. Okay, and so I guess before that's actually the end of what I wanted to say. Before I leave though, this is actually, I just want to note, this is for the real numbers, and Littlewood-Offord were actually interested in the same problem for complex numbers. And the same bound, n choose n over 2, is actually true for complex numbers. And that wasn't proven until the 60s, 1960s. I think like Katana, but I don't remember. And actually in 1970, do I have space to write this? In 1970, Kleitman showed that n choose n over 2 is the bound in an arbitrary so we can take any norm vector space. Yeah, I don't even think it needs to be finite dimensional. So any norm vector space could be R to the n, could be C to the n, could be C, obviously. Yeah, any norm vector space, this exact statement still holds, but the proof is a little bit different. It's actually not that much more complicated. It's actually in Bollobás in the same chapter. It's like 3 more pages than this. So maybe if, well, maybe if I get around to it, I might do a second video proving this one. But if not, I hope you liked this. I think it's a really cool theorem. And I hope you like this video.